In this section, we're going to take a look at two specific types of problems, we're going to call them. First is the area problem, and then the second is a distance problem. So the area problem is to find the area of the region S that lies under a curve y equals f of x on a closed interval from x equals a to x equals b. So if you have graph paper, you're probably going to want to use it for this section. If not, please make sure you have some sort of ruler or straight edge, but we're going to need to do some graphing. We want to try to be as neat and accurate as possible. So our first curve, or really line, that we're going to graph here is the line y equals 4. And we're only going to shade the area from x equals 1 to x equals 3. So actually, y equals 4 is a horizontal line going through 4 on the y-axis. Now, even though I drew this line this long, I'm only interested in kind of blocking this off from x equals 1 to x equals 3. So I'm just going to draw two vertical lines going straight down. Now, the area bounded by these x equals 1 and x equals 3, and then the horizontal line here, forms a nice rectangle because I'm also bounded by the x-axis. So I have a nice rectangle here, so I really just want to find the area, draw a little picture of a rectangle. We know the area of a rectangle is either length times width or base times height. So the base here is just the bottom, and that's only 2 units, just the distance from 1 to 3. So our base is 2, but our height is 4. So this is going to equal just 2 times 4. Now they are asking for area, so we have to label square units here. So when our area is formed into, or everything that's kind of bounding our area in is a nice geometry shape, we could definitely use a geometry formula. Okay, our second curve or line, again, is just that it is a line. We're going to take a look, though, when our curve is actually a curve and not a line. So our function here, we're going to start y equals negative 2x plus 6. My slope is negative 2, so I'm going to come down 2 over 1, down 2 over 1, down 2 over 1. So we'll go ahead and draw a line through these. Now again, I'm going to bound this by just x equals 0, so I'm going to draw a nice sort of a horizontal dashed line here showing that I'm going to start the area just going from x equals 0 to x equals 2. So I'm just drawing my area here. This is the region S that we're looking at. So this is the area we're looking at. So we no longer have a rectangle. What we actually have here is a trapezoid. So the area of a trapezoid is 1/2 times the height times the sum of the two bases. So in this case, our height is running this way. Our height is 2, almost as if you were to rotate your paper a little bit. Our first base is going to be this length right here. That's from 0 to 6. So base 1 is going to equal 6. Our second base, so the bases are what's parallel to each other. This is our second base, which is going to equal 2. Right here would be 2. All right, so as we fill this in, we're going to have 1/2 our height, which is 2, times the sum of our two bases, which is 6 plus 2. Half of 2 is just 1, so we're really getting another 8. Just a coincidence it worked out to be the same as the last one, so we get 8 square units. Let's try this one more time before we look at an actual curve. All right, our next example, we're looking at y equals negative x plus 3, so this is going to graph another line. Y-intercept is 3. We have a slope of negative 1, so I'm going down 1 over 1. And we're just going from x equals 0 to x equals 3. All right, so I'm looking right here, x equals 0 to x equals 3. This is the area I'm looking at. So if you notice here, we have a nice triangle. So we're going to write out that the area for a triangle is 1/2 our base times our height. So here our base measures 3. Our height also measures 3. So we're just looking at 1/2 of 3 times 3, which is 9 halves square units, or you could say 4.5 square units. It's perfectly fine to leave it like this. All right, so now in the next example, we're going to take a look at several different ways to figure this out. We're going to go ahead and graph y equals x squared. However, when you go to do this, let's space this out. So in this case, I'm going to count every 4 blocks is going to count as 1 unit along the x-axis. It's just going to make it nicer when we have to go to write on this. Every 2 blocks is going to count as 1 on my y-axis. All right, so again, when I go to graph, and I'm only going from 0 to 2, so that's why I'm not worried about any of the other quadrants. So 0 squared is 0, 1 squared is 1, and 2 squared is 4. And we want to try to draw this as accurately as possible, so as best you can, and it's okay if we're off a little bit too. So we just want to make this look like a parabola. So like this. Now, this isn't a nice geometry shape, so what we're going to do is make an approximation. So we actually call this, we're going to write out rectangular approximations. Eventually, we're going to have calculus help us out, but this is kind of like going through those long limit definitions of the derivative. We have to go through this part first before we could just turn this into a calculus formula to help us out. So there's going to be 3 rectangular approximations. The first is a left rectangular approximation measure. So the L stands for left, and I'm going to go over one of each of these. Next, we have a right rectangular approximation method or measurement. So we have an LRAM, what we call an RRAM, and then we have the middle rectangular approximation measurement. So we have an LRAM, RRAM, and MRAM. Now, a lot of times too, we have to be given how many intervals we want to make, or subintervals. So we're going to use 4 subintervals here. That tells us how many rectangles we're going to make. And then what we end up doing is adding the areas of the rectangles, and that's why it's an approximation. We know how to work with areas of rectangles, so we're going to try to do that to approximate this. And this is known as the Riemann sum, named after a mathematician. All right, so what we're first going to calculate is an LRAM. This just means the heights of each rectangle are determined by the left endpoint of the rectangle here. So I'm going to start at 0. Now, 4 subintervals, I'm counting over to 2, so I have to make these into quarters. So my first rectangle is only going to go from 0 to 1/2. My second rectangle is going to span from 1/2 to 1. My third rectangle is going to fit in from 1 to 3/2. And then from 3/2 to 2 is going to be my fourth rectangle. So right here at 0, 0, that's the start of my first rectangle. Well, that's right at the x-axis, so actually my first rectangle is flat. It has no height to it. It has a base, but it has no height. What I'm going to do from there is go straight up to where I'm on the curve, and then I'm going to go over, straight over to the 1 and go down. That's my second rectangle. From there, I'm going to go up, and then I'm going to go over, and then from there, I'm going to go up, and I'm going to go over. Now, my graph isn't the most accurately drawn, so we're going to rely on the curve here, y equals x squared, to help us out. I need these points. So obviously, right here is the ordered pair 0, 0. This 0 is telling me the height of my rectangle. Next, it does look like it's 1/2, 1/2, but it's just because I didn't draw it the greatest. This is actually the ordered pair 1/2. Now, if I square 1/2, it's 1/4. This point right here is the ordered pair 1, 1. And that's what I get. If I square 1, I get 1. Right here, if I square 3/2, I'm actually at 9/4. So if you do notice, I'm a little bit above the 2. So 0 is the height of the first rectangle, 1/4 is the height of my second rectangle, 1 is the height of my third rectangle, and 9/4 is the height of my fourth rectangle. So under the LRAM, we're going to say the area is approximately, that's another symbol for approximate, my area of my first base. Again, my base is going to be the area of my first rectangle. My base is going to be 1/2. My height is 0. The second rectangle, my base again is 1/2. My height is 1/4. My third rectangle, again, my base is 1/2, my height is 1. And then my fourth rectangle, my base is 1/2, my height is 9/4. So we're going to add these together. And yes, it's okay if you use a calculator. I want to turn this into a decimal anyway, but I tell you what, this first one we really don't need a calculator. 1/2 times 0 is just 0. Then I'm going to get a 1/8. Then we're going to get a 1/2. And then we're going to get 9/8. So if I were to add 9/8 and 1/8, that's 10/8. And then I could really say plus 16/8. So I'm going to get 26/8. Or we could say 13. Sorry, that should have been 4/8. A 1/2. I was thinking of 2. So we're going to get 14/8 or 7/4. So then this is 1.75. And again, we're talking area here, so we want square units. So if you notice where these rectangles came with respect to the curve, they were definitely below it. We had some gaps, so we had some area that was not filled in. So this is definitely an underestimate. So that's why we kind of go through these three. So let's take a look at the right rectangular approximation. Let's go ahead and reconstruct the graph. Again, I'm going to go over 4 units here to count for 1, another 4 to count for 2. I'm still just going to number by 2 here. We're still going to do 4 sub-intervals, so I still want this to be 1/2 and then 3/2 in the middle. Now we could draw this a little more accurately too. So here's like our 1/4, and then here's our 9/4. So we have more points to kind of go through here. All right, so this is still the graph of y equals x squared. So now when we go to make the rectangles, we're going to start the right upper corner is going to be where it touches our curve. So for my first rectangle, I'm going to go straight down here and I'm going to go over. So notice it's the upper right corner of the rectangle that touches the curve. Next, I'm going to go up to 1. And then if I go over this way. So now these rectangles are sitting above the curve. Same thing here for the 3/2. I'm going to go over. And then likewise for the 2. So there's my rectangles. And again, let's go ahead and write out the ordered pairs. I'm no longer going to start with my first rectangle here at 0. It now has some height. I want this ordered pair. So remember, that was 1/2, 1/4. Right here is 1, 1. Right here is the 3/2 and 9/4. And then last, I'm now including the 2, 4, because 2 squared is 4. Where before I started with the 0, 0, and I didn't have the 2, 4. So we're using the right upper corners. Those are going to be the heights of our rectangles. The widths are still 1/2. So now I have 1/2 times 1/4 for the area of my first rectangle, plus 1/2 times 1 for the area of my second rectangle, plus 1/2 times 9/4, area of my third rectangle, and then plus 1/2 times 4. So this will give us 1/8 plus 1/2 plus 9/8 plus a 2. So I'm still going to get 10/8. We could say plus 4/8. And here's my 16/8. I wanted so badly in the last problem here. So now if we add this together, we're going to get 30/8. Again, let's turn this into a decimal. So 8 is going to go into 33 times. That'll still give us 6/8 or 3/4. So we can still say at 3.75 square units. Now, because these rectangles sat above, this is an overestimate. So where Not that close to the LRAM. We got a 1.75 square units for that. Now we're a little too over 3.75. So somewhere in between 1.75 and 3.75 is going to be the exact. So let's try this with the MRAM. This is where the heights of the rectangles are the midpoints of the heights. That's where it's going to touch the curve. So again, let's go ahead and mark these. Here's my 1 and my 2. So yes, we do have to graph this another time. I still want to mark the 1/2, the 3/2. And again, this is our graph y equals x squared. All right, so I already used the left point. I'm not using that again. I already used the 1/2. We need to go right in the middle, so we need these markings. I need the 1/4. You think of 1/2 is 2/4, so right in between 1/2 and 1, there's my 3/4. 1 is 4/4, so after that I'll have a 5/4. 3/2 is 6/4, so after that I'll have a 7/4. So that's where we're going to make our points. I'm going to go up just on the graph right above each of these and make the point. So now the rectangle is going to come out from either side here. So I'm going to have a little bit over and then a little bit under. So here's my first rectangle. Next, I'm going to do the same thing. Start from the midpoint and go over. So here's my second rectangle. I have a little bit over, a little bit under. We'll do the third. A little bit over, a little bit under. And then the fourth as well. All right, so here, again, we have to find the ordered pairs. So this one right here, this is going to be the ordered pair 1/4. And again, all I have to do is square the 1/4, so I'm going to get a 1/16. Now, if this said y equals x squared plus 1, which is an example I'm actually going to do in class, we would just take 1/16 and have to add 16/16. So you're going to get a good amount of work with fractions in this section. The second point right here is 3/4. Square that, we're going to get 9/16. This point right here is 5/4. Square that, we're going to get 25/16. And then right here we have 7/4. Square that, we're going to get 49/16. So our area is approximately, still our base is 1/2 times 1/16. That's the height of our first rectangle. Plus the base of our second rectangle is still 1/2. Our height is 9/16. Plus the base of our third rectangle is still 1/2. Our height is 25/16. Then our last rectangle, still the width is 1/2. Height is 49/16. All right, so we're going to get, at least this way we have all of our denominators are going to be the same. We're going to get 1/32 plus 9/32 plus 25/32 plus 49/32. So we can still add all of these up together. Go ahead and do that. Turn it into a decimal as well. We should be getting 84/32. We can divide both of those by 4, it looks like, so we're going to get 21/8. We could turn that into a decimal. So this is turning out to be 2.625 square units. That's definitely in between the 1.75 and the 3.75. So that's very close. That's a better estimate of, so I kind of put this here. This is the best estimate out of all three to use. Again, LRAM is a little bit under, RRAM is a little bit over. Here, this is probably the closest because we have a little bit over, a little bit under. What could also help is creating more rectangles. We're going to try this one more time, still with an LRAM, but we're going to make 6 subintervals. So that means I need 6 little marks. So I'm going to count every 3 blocks here are going to be 1 measurement along the x-axis. I'm still going to count by every 2 blocks here is going to count as 1 unit. So again, I'm going to graph y equals x squared. Start at 0, 0, 1, 1, and 2, 4. So because I want 6 subintervals, this is why I chose 3, because now I'm going to have to count by 1/3 here. Then I'll have 2/3, 3/3 is 1, we'll have 4/3, 5/3, and then 6/3 is 2. So we are going to try to squeeze this in a little bit here. So I'm going to do an LRAM. So it means, again, I'm going to start with 0. I'm going to make my first rectangle. Notice now my width is the 1/3 instead of a 1/2. So my first, we're going to write out, area is approximately 1/3 times 0. I have no height there. Next, I'm going to go up, create my second rectangle. So this is the point, 1/3. Square that, we're going to get a 1/9. So next I'm going to have plus 1/3 times 1/9. My next point is going to start here. My left end point, I'm going to go over and then down. So this is 2/3. Square that, we'll get 4/9. That's that third point right here. So I'm going to have 1/3 times 4/9. Right here, I still have the point 1, 1. So that's going to be 1/3 times 1. For my fourth rectangle, I'm going to go straight up from that and then over. So this point right here is 4/3. Then I'll have 16/9. So we'll have plus 1/3 times 16/9. And then my sixth rectangle is going to meet right here. And then this point right here is going to be 5/3 and then 25/9. All right, so if you notice, we should have 6 parts written out here for the 6 rectangles that we're looking at. So again, that's going to give me a 0. I'm going to have 1/27 plus 4/27 plus 1/3 plus 16/27 plus 25/27. All right, just go ahead and use a calculator to get this all into a decimal. All right, so I did just add all the fractions with denominators of 27. I turned that 1/3 into 9/27. So we're getting 55/27, or approximately 2.037 square units. Now this is the LRAM. If you remember the LRAM with 4 subintervals, that came to 1.75. Look at how much more we increased now. So we're getting closer to what that middle our MRAM was actually showing us here. So the more rectangles we have, the more accurate we're going to be, or closer we're going to be with our approximation to the exact. So to actually find the exact area, which, like I said again, we'll eventually use calculus, this is relating it back to the Appendix E. So if you didn't watch Appendix E, if you didn't watch that video yet, please make sure you do. We looked at some limits here using this sigma notation. So this is saying the limit as n keeps increasing without bound. N is the number of rectangles we're using. So the more rectangles we fit in, the better approximation we're going to have. And if n keeps increasing without bound, if we have an infinite number of rectangles, we're going to have the exact area. This is just telling us to add everything up from I equals 1 to n here. The f of x, remember, anytime we were looking at f of x, that was the height of the rectangles. And then this delta x here, that's the width. So when we do height times width, or base times height, it doesn't matter. This is just the area. So we are adding the areas of the rectangles. And if we can squeeze in an unlimited number, an infinite number of rectangles, we're going to get the exact area. So like I said, eventually we're going to take a look at this. And just to point out, let me go back to the exact area for this problem. I'll show you soon enough how I was getting this, is approximately a 2.67. So when we go back and look at that MRAM, it was a 2.63. So we were very close to that. We were using the best approximation with that one there. All right, so last we're going to take a look at the distance problem. So this is pretty much going to turn out to be the same type of problem, only we're not looking at a graph, we're going to be looking at a table. But the distance problem is to find the distance traveled by an object during a certain time period if the velocity of the object is known at all times. So to figure out distance, we do rate times time, but in our case, the rate is our velocity, so we do velocity times time. That sounds a lot like base times height, doesn't it? So this means we're going to create rectangles in a way without actually creating them, but we're going to look at a graph here. So it's like the ordered pairs were already given to us. So this first example, we're given a speedometer, just speedometer readings for a motorcycle at 10-second intervals. They're given to us in this table. So the time seconds, this is like the base of our rectangle, and the velocity would be our height. What's going to change, though, what we're going to be asked to do is to find them at like the left endpoints and then the right endpoints, or the beginning of the time interval or the end of the time interval. So our time in seconds just goes from 0, 10, 20, 30, 40, 50. So in 10-second intervals, here's the velocity at those in feet per second. So if you're thinking, man, that motorcyclist is going slow, this is in feet per second. So for A, we're going to estimate the distance traveled by the motorcycle during this time period using the velocities at the beginning of the time intervals. So we're going to calculate, instead of area, we're going to say distance. So I'm going to say D is approximately, if I'm starting at the beginning, that means I do 0 times the 25. I'm sorry, not the 0. The width here is the 0 to the 10. So each width is going to be 10. So let me go back and mark that up here. Each base is going to be 10. Because that would be like starting from 0 to 1/2. So each distance, the base is going to be 10. Now we're going to start with the 25. Plus the next width, or the base here, would be 10. Then times the 22. We're going to have another 10 times the 18. And we're going to go 10 times 17. And then 10 times 20. And again, yes, you can use a calculator to come up with this. All right, so again, this is distance, so distance would just be in feet. So we're looking at 1,020 feet as approximate total distance traveled. All right, and then for example B, we're going to do the same thing, but now we're going to use the velocities at the end of the time period. So this would be like the RRAM. What we did in A would be like the LRAM. So instead of starting with the 25, we're going to start with the 22 and end with the 21. Again, the width is still going to be the 10. So here we're going to say our distance is approximately the 10 times the 22 plus 10 times 18 plus 10 times 17 plus 10 times 20. And then our last one was plus 10 times 21. And again, go ahead and calculate that. And then this should be giving us 980 feet. So this is how we could find total distance traveled given the velocities and the times. Now we could find the exact distance again. In this case, this would be written out as the limit, again, as n increases without bound. The summation as I goes from 1 to n of f of, instead of x, we're just going to use t because we're using times, and then delta t. That's the change in times. So again, this would be the velocities at each time interval. And then this right here is the change in time. That was like our 10 seconds. Now this part right here, if we put this all together, this actually turns into, and I'm going to kind of give it away right here, but this becomes, as n keeps increasing without bound, or we write the sum, we can write it in a much shorter notation. So this actually becomes this symbol. It looks like a stretched out S, but it's actually the symbol for the integral. And we're going to write this as we're looking like from A to B. So it's the integral from A to B. We'll write here of f of t, that's just this part right here, times delta t here, we could just write dt. Or we could say the integral from A to B of f of x dx. And this is much shorter notation. We no longer have to worry about sigma notation or the limit. This is now what we're going to be using in the upcoming sections. So that wraps up section 4.1.